Today we're going to start a series that will go into our refrigeration cycle course for understanding more about the refrigeration cycle and sort of the intricacies and so on. And we're going to start with the evaporator because moving heat is the purpose. And as you can see, that's the name of this presentation, moving heat is the purpose. And that's the whole purpose of the HVAC or the air conditioning or the refrigeration cycle. It's the whole purpose is to take heat from where it is not wanted and put it where nobody cares. Remember, heat goes from hot to cold, and the greater the temperature difference, the faster the flow. So, this session is all about transferring heat into the refrigeration cycle. And I've got images up here. I've got 3 air evaporators or evaporators used in Airstreams. Obviously, copper coils, aluminum fins on the coil, and so on. You guys have seen these, you know what they are, etc. All these are fresh coils. There's no metering devices on them at this point. And then I've got a chiller barrel here and a chiller barrel there, showing it's essentially the same thing in the water cooling business. Is you have to get a refrigerant system in the chiller barrel where you have an evaporator tubing. You got to get that refrigerant colder than the water coming in to get that heat to transfer out of the water into the refrigerant that's in the evaporator side of the system. So with that, I just want to put this up real quick. In our course, you have access to this animation, and so the rest of this presentation is based on this animation. If you're in the course, you'll have access to this animation. You'll have to open it up, and then you'll have to energize it. You energize it by turning the switch to cool, just like you would in real life. You've got to turn the thermostat down. You've got to select it to cool, and then you've got to turn the temperature down to 75. And that starts the system going, all right? And you can see down below here we have a runtime counter. Starts at 0 and goes up to 300 seconds. That's a 5-minute run. This is specifying that the outdoor temperature is 95-degree ambient, which is the rating point for unitary air conditioning products. AHRI rates air conditioning equipment at a 95-degree ambient. So I just threw that in there just for that purpose. Give us a standard. Another feature is we've got a temperature thermometer here, electronic thermometer with a temperature probe. You can take that temperature probe and move it around and measure temperature on the electronic thermometer. You can see the temperature changing up here and so on. So this is a tool that we have built for you to use so that you can get a good handle on the refrigeration cycle without sitting somewhere and trying to learn it the hard way. This is the easy way. You'll learn it the hard way plenty of times. Read the instructions and use it to develop your understanding of the cycle. It works great for that. You've got 15 points, and you notice these points are all throughout the cycle here, all these little gold numbered buttons. Those are the 15 measurement points that you can measure with a temperature probe, so you can drag it around and measure and so on. And like it says, you can't know enough about it. If you need help, click the help button, and that's when you're in the simulation. As well as there's a whole set of instructions for this as you go. So, to cause heat to flow into the refrigerant inside the evaporator, the condition of the refrigerant must be colder than the air or water flowing through the fin and past the fin coil, i.e. whether it's the water, chiller barrel, or an air coil. Heat goes from hot to cold. Once again, the coil is normally made of copper tubing because copper is great conductor of heat. Go figure, right? So, in this case, when you're trying to move heat and you're trying to get heat away from somewhere, you don't want to slow it down, so you use materials that conduct heat the best. And copper is one of them. Copper is a great conductor of heat. So is gold, by the way, but I haven't seen too many gold evaporator coils, at least not in my service calls. So this image shows the starting point of the cycle. Nothing is running. If that compressor is not running, nothing else is going to happen. The inside air temperature must be 78 degrees. And why do I say that? Because I've got the surface probe here on point number 10 at the inlet of the evaporator, and my thermometer is telling me it's 78 degrees. That means that the saturated condition of the refrigerant inside the evaporator is at the same temperature as the air around the evaporator. And before you start up a system, that's exactly true. A refrigerant is a great measuring device, if you will, to tell you what temperature the ambient is. If I have 78 degree air around a refrigerant tank, the pressure temperature relationship of the tank will be at 78 degrees because it's in a saturated condition. There's no pump, Nothing is happening. It's just sitting there static. All right. So how do you use this thing? Well, I just demonstrated real quickly, just previous to this. A couple of things to know. These service valves on this simulated animation, you click on them, and then you select cracked off the back seat so the gauges will read. And you want to do that before you start it, because otherwise you'll be looking at a dead gauge. It won't say anything, and your compressor will be running, things will be going on, and you'll be sitting there going, why aren't my gauges reading? Well, it's because you've got to crack them off the back seat, just like you do in a regular system. You can drag this probe around to wherever you want to measure, and it'll give you the temperature on the thermometer over here. You have to turn this to cool. You have to select cool in this thermostat, and you have to turn down the temperature to get it to run. There is a extended set of instructions as you go into the simulation. There's like a 2 or 3 page exercise instructions. Make sure you read them. We're going to start at the beginning of the cycle. And here is the beginning. So we are focused on the evaporator. So the only thing you're going to see as I go through these zillion slides, because that's what we're going to do. We're going to go through a zillion slides. We're going to look at the beginning of the cycle, the middle of the cycle, and the end of the cycle. What you need to recognize when you're looking at a refrigeration cycle is that it transitions totally from the time it starts to the time it finishes doing the job. In this case, we have the thermostat right here set at 75 degrees, so we want to go to 75 degrees. That would be the end of the job, or as I usually say, that's the end of the load, because what we're doing is we're pulling a load of heat out of this space, a residential place or an office building or whatever it is. We're starting here, and as you notice down below on the run time, we're 15 seconds into the run. So what that means is we just started this system. We're only 15 seconds into the run, so it just started. All right? And what happens when you just start a cooling system? If you remember, the temperature in the previous slide was 78 degrees, the air coming into this thing right there, 78 degrees inside air temperature. All right? So that's where we're starting. Notice the thermostat says 78 degrees as well. The temperature probe says 78 degrees. So everything was static at 78 degrees. So we're just started. And that's important to know. When you walk in and look at a refrigeration cycle, if it's been running for a while, one of the things you want to know is, okay, so about where are we in the cycle? Did we just start? Are we halfway through? Are we getting close to pulling the load? What's happening? What's going on? Because that will tell you a lot as you're looking at it. And remember, we are just doing a normal cycle. I'm not going to throw any bugs into this thing yet. All right? So, and we're also focused on the evaporator. So here I am. If you're at the start of the cycle, what that means is you have the greatest amount of heat available in the airflow. In this case, we're using air. In the airflow going around this evaporator coil. So we have the biggest amount of heat available to grab. Since we're in a capillary tube system, that means we're getting X amount of refrigerant through the metering device, and there's not really any way to throttle more in, like a thermal expansion valve or electronic expansion valve. They would be throttling more refrigerant in based on the exit temperature of the evaporator out here on the suction line. That's where the sensing bulb for the thermal expansion valve is clamped, and also where the sensor for an electronic expansion valve goes is on the outlet of the evaporator. But we're dealing with a cap tube, all right? So let's run through this. We're at point 10. We're 15 seconds into the run. We have the highest level of the load. Suction is at 94.2 right here. You can see it in the big window, and you can also see it here in the suction gauge. Saturated temperature is 56 degrees. If you look down here, I've got the pressure temperature chart shown here on the screen. 94.2 PSIG is somewhere around 56 degrees. One thing to say about pressure temperature charts, not all charts are created the same. As I was putting this together, I had an Alco, I think it was an Alco pressure temperature chart on the desk with me, and I was looking at that chart and comparing it to the Suva DuPont chart. And I was sitting there going, oh geez, you know, they're a little bit off here, a little bit off, they're different, all right? But the important thing to recognize is everything's going to be different. How accurate are your gauges? How often do you adjust and calibrate your gauges? If you don't do that on a regular basis, they're going to be a little bit off. How accurate is your electronic thermometer? How often do you check it for calibration? How often do you give it a 32-degree bath to see if it says 32, et cetera, et cetera? So we, fortunately, and by and large, we do not have to be down to the gnat's eyebrows accurate with our measurements. You want to be as accurate as possible, but recognize there's a little bit of twist here. So I'm saying that our suction is 94.2, which I'm reading right off my gauges. That tells me, based on this pressure temperature chart, that I'm at 56 degrees Fahrenheit, saturated condition. The inside temperature going in is 77.5. I'm measuring right here at the inlet of the evaporator. And I will tell you that if you have a system running, if there is any saturated condition anywhere, it's going to be at the inlet of the evaporator, because that's where the first liquid comes into the evaporator, comes into that space. You've had the pressure drop through the capillary tube or the metering device, and it's at 94.2 pounds in there. Boom, the R22 is our example. R22 is going to flash off and evaporate at 56 degrees Fahrenheit. If you ever want to check saturated condition, or even better, if you want to check the type of refrigerant that might be in the system, as long as it's not something somebody mixed, you go right to the inlet of the evaporator, you're running the system, you're taking the suction pressure, and you should be able to determine what type of refrigerant's in there, because if there's a saturated condition anywhere, it's going to be at the outlet of the metering device. You can't miss. So what does that mean? I've got 56 on the temperature probe. I've got a saturated condition of 56 off my pressure temperature chart. That means my superheat is 0. Remember, superheat is measured temperature with a surface probe minus the saturated condition, and that tells you how much temperature or how much heat above the saturated condition you have in the vapor.